In the panel, the tranny tube lengths are shortened to ensure that fresh concrete as bentonite is pumped back to the lifted off the bottom of the excavation so that the concrete flows out, displacing the lighter bentonite mud upwards. The bentonite is pumped back to the recycling plant as it's displaced. As the concrete level rises in the panel, the tranny tube lengths are shortened to ensure that fresh concrete is always closest to the concrete bentonite interface. When the concrete rises to the required level, the tranny pipes are removed and the concrete is allowed to set. The first panel, constructed in a run-of wall, is called the primary panel. During concreting, the excavation grab and base crane is moved to another location, a safe distance from the concreted panel, and excavation recommenced on another primary panel. The next excavated panel is completed and concreted in the same procedure as just described. Subsequent panels excavated adjacent to a completed panel are called secondary or running panels. The final panel concreted in a run-of wall is termed the closing panel, as this panel closes up the length of wall. The stop end is removed from one panel during excavation of the adjacent panel. Diaphragm wall panels can be excavated using several types of equipment, including hydraulic cutters. These are powerful machines capable of excavating into hard rock, but require large bentonite plants and large cranes to hold the cutter. Steering mechanisms are built into the grab body to provide a high degree of verticality control. The hydraulic grab. This type of grab has hydraulically operated closing jaws, and so is able to exert considerable closing force to excavate dense sands, stiff clay, or weak rock material. These grab bodies can also include steering mechanisms. The cable grab. This grab uses only pulley forces to close the grab jaws, and so is more suited to softer ground. And the Kelly grab. This grab type is rigidly suspended from the base machine, whereas the three previous types are rope suspended. The Kelly grab can provide reasonable excavation force and verticality control, but may not be as fast as suspended grab excavation. Typical diaphragm wall widths are 600 millimeters, 800 millimeters, 1200 millimeters, and 1500 millimeters, though other sizes can be used for special requirements. Piling contractors.
So these were your different equipments which are used for excavating the ground, or you can see for the hard rocks also when you're excavating to construct the diaphragm walls. This can be your hydraulic cutter, which you will have a large what is it called, uh, these cutters are here, you're looking here and here, this white ones also. These will cut out your soils or the hard rocks also. It can cut your hydraulic cutters. Bentonite, but here what will happen, your bentonite plant will have to be a large bentonite plant has to be there, so that the bentonite slurry is automatically it is faster, because automatically your bentonite slurry will be given here, then again next portion will be done, then again bentonite slurry will be given. Okay, so this is the faster one. And hydraulic jacks and etc can be used, machines can be is used here. But again, the other three crabs, these are your crabs, which are, you see this portion, these are like crabs, they are holding your this portion, the soil or the rock, and then they take it and then they move upward again, then again comes down and again takes up some soil or the excavate some, and then again moves up. Similar to this is this one and this one. Okay, but here in this hydraulic crab, what is happening here, their cable is there, but it is hydraulically, it is moved forward and moved backward. Okay, we're using the hydraulic machine. But here in this one, same, this is also a crab, but it has a cable. This also has a cable, this also has a cable. Hydraulic crab and the cable crab both has the cable, but here it is hydraulically controlled. These are holding from the top with your hydraulic machine, and here only the cable is there, and due to this only one cable hanging with the crab, what is happening, obviously your this with this equipment will move here, here, it will move like a pendulum also sometimes when you obviously when you move your this longer cable with the crab, with this cable crab here at the bottom, as much deep you are going, this will keep on moving like this. So what will happen, some soil will be taken out from here, then again some little soil this side, it is verticality is not maintained. Okay, so it's little bit difficult in that case. But here in the third one, the cali crab, what is that? Cali crab is also same, these three are almost the same one, like a crab. But Cali crab is what, these doesn't use any cables. Here also cable is was here. Hydraulic crab and the cable crab both had a cable, but this additionally had a hydraulic equipment added to it. But here in the Cali crab, here there is no cable. Instead of a cable, pipe kind of this is joined to the crab, so that the verticality is maintained. However, here what happens, it will take more time as compared to these, the first, second. Okay, why? Because verticality is maintained, but it takes up lesser amount of your soil or the hard rock, whatever you are digging for your this construction of your diaphragm one. First one diaphragm wall will be constructed panel, then another panel of the diaphragm will be constructed, then third panel, then fourth panel. Okay, so these are your the second, third, these were known as what, your secondary panel. This were your primary panels, the first and the last ones. Okay, named as your primary, the beginners and the end one, and in the middle those panels which are set up for your diaphragm walls, what is that, they are your secondary walls. Okay, so now we'll talk about the tunneling. Wait. We'll just look a video on your tunnel construction. Okay, after that I'll show you the drilling ones, how it is done, jumbo drill, etc.
World's great mass transit systems, and the means by which we move waste away from urban areas. Tunnels are among the most critical pieces of infrastructure that keep our cities moving. However, unlike above-ground infrastructure, which becomes a visual part of any city upon its completion, the scale, engineering complexities, and methods required to construct and operate our tunnels goes largely unnoticed by the millions of people who use them every day. From digging in the dark to ensuring safety, minimizing disruption, and bringing fresh air underground, these are the critical challenges that must be overcome to make our world's tunnels a reality. The methods used to build the majority of today's tunnels mean that, aside from a number of scattered access sites across their routes, The work to form these structures goes largely unnoticed by the population. By contrast, the earliest tunnelling method, known as cut and cover, was one of the most disruptive processes a city had to endure to construct vital below-ground infrastructure. With this method, engineers would first dig a trench, then lay bricks to form the tunnel walls, before backfilling the excavation and reinstating the surface above. This approach required large stretches of the streets above to be closed for extended periods, creating congestion. In some instances, properties along the route had to be acquired before works could proceed. The cut and cover technique was used to construct London's Metropolitan Line, the world's first underground railway route. The impact of the work to form this line can still be seen today in the numerous sections of track that have been left exposed, where buildings were not reinstated on completion. Today, tunnel boring machines, or TBMs, are used to construct tunnels in urban areas, eliminating much of the disruption that tunnelling schemes caused in the past. Operating on the same basic principles as the tunnelling shield developed by Sir Mark Isambard Brunel during the construction of the Thames Tunnel in the 19th century, TBMs are able to excavate material and line the tunnel that they form in one continuous process, increasing efficiency and greatly improving safety. Due to their size, varying between 150 and 200 metres in length, TBMs need to be delivered to their entry sites in pieces before being lowered into access shafts and assembled. While variations of TBMs exist for different soil types, the key piece of machinery common to all systems is the forward-facing rotating head, which is lined with a series of blades able to cut through all manner of rock. Spoil from the excavation is funneled behind the cutter head and transported back towards the tunnel entrance via conveyor belts. Much of the spoil from the construction of London's Crossrail, one of the world's largest infrastructure projects, has been transported to the Thames estuary and used to create a vast new wetland sanctuary. As the TBM moves forward, precast concrete shells are brought in to form the lining of the tunnel behind it, preventing the surrounding earth from collapsing back. Due to the costs and logistics associated with removing them, many TBMs, like those used to construct Channel Tunnel, are simply driven off into the earth and left in place once they complete their work. However, in recent times, and with their costs increasing, a number of schemes have removed their boring machines on completion, ready for use on future projects. While the physical construction of a tunnel is a considerable engineering feat, the ongoing operation and management of these structures can be just as challenging. Regardless of their use, monitoring tunnels throughout their lifespan to ensure their ongoing safe operation is paramount. Ventilation is critical, particularly with road tunnels where high levels of pollutants, including carbon monoxide and nitrogen oxide, are continually discharged. Numerous methods are used to improve the quality of air in tunnels. While some systems force clean air through these underground spaces, others focus on the extraction of pollutants through ventilation ducts, which in turn draw fresh air in. We've used SimScale to simulate how such a system works on the Central Artery Tunnel project in Boston, a scheme which reroutes the central artery of Interstate 93 through the Thomas P. O'Neill Jr. Tunnel. With more than 150,000 users worldwide, SimScale is an easy-to-use cloud-based engineering simulation platform that enables everyone to create powerful, high-fidelity simulations in a web browser. The platform can be tried for free through the community account, which gives access to thousands of public simulations, promote knowledge sharing, and to crowdsource advice. The ventilation techniques used in many tunnels work in tandem with fire suppression systems to clear smoke in the event of fire. Within road tunnels, extensive traffic management and signalling systems are in place to reduce the risk of accidents between vehicles, which could bring operations to a standstill in a considerably confined space.
For motor vehicles, electronic displays provide up-to-date information to drivers on which lanes are in use and alert drivers to obstacles ahead. It is also typically forbidden to change lanes while travelling through tunnels to minimise the risk of incidents between vehicles. Many road tunnels also feature traffic control systems outside of their entrances to prevent vehicles sitting stationary in congestion once inside. In the case of metro tunnels, sensors on trains and signals through the length of a tunnel's route alert drivers to the status of other trains ahead, allowing them to remain on the platform in the event of incidents. In the unlikely event that these systems are unable to prevent an accident within the tunnel, emergency systems alert drivers and passengers to abandon their vehicles and proceed to the nearest refuge or escape point. In addition, many modern tunnels are now built in pairs, with traffic travelling in a single direction to further reduce the risk of a head-on collision. This approach allows passengers to pass through to the safety of the alternate tunnel in the event of emergency. Though they often go unnoticed, tunnels are, in fact, the arteries that power our cities. Passing beneath our feet and transporting millions of people every day, these critical pieces of infrastructure are truly in a world of their own. If you enjoyed this video,
So this was your just a simple explanation on your tunneling. Okay. Let me hello. Okay. So this is the underground mining, one of the practicals shown here for your drilling jumbo. Okay, this is drilling jumbo. These are your jumbos which are used to drill. These are the rock, you can say, which was drilled and then moved out for the construction of the tunnel. So how they are used? Hmm? This one. Hello. Okay, now these are your drillings jumbo. They'll be drilling this portion. Okay, see how it is made. Drilling will be done here. So this is your there are some different techniques of your tunneling. So one of them is this is the drilling jumbo, where it is used to drill the rock here, you see, and then what is done by drilling you can make it, and then you can blast this portion, and then you can again cast this, you can give the reinforcement here, then again the concreting you can do, then again this will be blasted, again you'll the same, repeat. Okay, so I'll be showing you one for 160 seconds that video where you will see that how it is drilled in this way, and then it is done. That is your drilling and blasting technique. Okay, with normal drillers, but then again this is your jumbo driller. So based on this machines also your types can be defined. So I'll show you another one. Wait. Now for the 60 seconds one, where you will see the drilling and blasting. Okay, I'll share my screen now. Drill and blast. This technique is your drill and blast tunneling in 60 seconds. How the drilling which we for drilling we had used what? We had used the jumbo driller. That's why it is jumbo drilling. Okay. Otherwise, too, nowadays we the before the first video where I showed you the tunnel boring machine was used, TBM machine, the huge TBM machines, 100 meters of diameters. Those were used for normal automatic this thing, for the automatic tunneling portion. Wait, just give me a second. Someone is calling. I think my network was gone. I was hanged. Okay, so let me. I have shared my screen just for 1 minute now. Just see how this drilling and blasting is done. Okay. What happened? Hello? Am I audible? Can you listen the video?
Yes, ma'am.
Video sound, are you able to? Hello? Hey? Hello? Hello? Is the screen visible to you all?
Yes, ma'am.
But it's not starting. Till then, let me to. Okay, I think this video is not starting. So I'll share you the link attendance, give you attendance there. Let me share the attendance link. Wait. Um, Building construction. 262. Okay, give you attendance. Go to the link and give you attendance there. 262. Okay, after giving your attendance, you can go and join the next class.